Hi everyone, I'm Dan Dokipen Elliott, and it's been a while since I made a video. So what I'm going to be doing in this video is just taking you on a bit of a walkthrough through some of the experiments I've been doing in terms of the real-time fluids in Unreal Engine 5. I haven't made a video in a while because just work commitments and family commitments. So hopefully I can start just kind of making more videos like this where I just prepare them less, just record, talk, and hopefully you'll just get to see more stuff and I'll get to make more videos. Let's lower my desk a bit. Okay, so here we are in Unreal Engine 5, and my frame rate might be a bit lower because I am actually recording the screen at 4K, so let's turn that off. That might help make this a bit smoother. So what you're seeing here is a 2D smoke or fluid simulation in Niagara, and also a 3D ray marching shader where the shadow pass is being done in Niagara. And I'm going to be talking mostly about this in this video, and then I might do another video where I talk about how this one was done. So let's just dive right into this. Well, first of all, I should probably say that the reason that I kind of got into this area is because I saw a video by Andreas Glad, who's a tech artist, and he has a nice YouTube channel which showed how to get started with Grid 2D in Unreal Engine in Niagara. And that was kind of the stepping stone I needed to be able to get into Niagara, because I'd been meaning to get into it for quite a while, but it was just kind of slow going and kind of wasn't going into the brain as quickly as it should. But this video really kind of gave me a nice kind of leap into what I needed to know to be able to get stuff done. And other people that have kind of influenced me in this area, Ryan Brooks, who works for Epic Games, and he's a tech artist there, and his blog post on volumetric ray marching is a really good post, and this is what I based my ray marcher on, with a lot of these kind of nice improvements in quality due to these kind of tweaks that you can do to increase the, well, you move your sample positions, things like that. And he talks a bit about how to remove some of these artifacts. And then I've been talking a bit with Andres Ketzer, who's the author of Fluid Ninja. It's a plugin for Unreal, which does 2D fluid simulation. So he's put together a nice little plugin package, and you can get that on the marketplace. So my experiments have been mainly in this kind of area of 2D simulation in Niagara. So here's the actual graph itself, and here's all the simulation stages. But what I'll do is I'll walk you through how I got to this stage by kind of walking through the different particle systems or Niagara systems and building each kind of component layer by layer. So here we have the first kind of thing that I came up with, which is just emitting stuff into a 2D grid and having it advected. And I'll explain what that all means. So the way that you create a grid is, at first it was a bit confusing for me how that is done, because there are actually several ways you can do this. You can create them. Actually, what I'll do is I'll create a blank system so that you can actually have a look. I think I've got one here. That was me practicing this earlier. So let's say you have a Niagara system with nothing in it. It's an empty system that you created, and then you created an empty emitter just by going to here and add an empty one. You've got this kind of like bare minimum state here that you're provided with. You can create a grid 2D up here in the emitter attributes. You can hit the plus button and you can create a grid 2D collection this way. So now we have a grid 2D collection on this emitter, as well as all the other kind of attributes that are there for just maintaining the general state of the emitter. There's also ways you can do it here. So if you come to the emitter spawn, when the emitter is spawned, we're going to use this set new or existing parameter directly module, and right now it's not setting anything, there's no parameters, but you can also use the plus button here and you can use that to create a grid 2D collection, which when you first do this, you'll get this error saying that there's no actual value, a valid value. But if you just click this fix issue, what it will do is it will create like a default one for you, like inline here. So this is kind of like a local one that's being created, and then that will kind of just kind of get added to your emitter, and everything else can use it further on down the line. So here you'd create your resolution, that kind of thing. You can also create render targets. It looks like you can actually use render targets as the backing of a Grid 2D collection. I'm not quite sure about how this works, but it basically is a texture under the hood. So here you can come up again, and let's say we wanted to create a render target which we wanted to feed to a material to render to. You get the same thing where you can click fix issue, and it will create a default render target for you. It would be nice if you could actually control these with inputs from, say, the actual system itself, because right now you have to input these manually, where it would be nice to have a kind of a global parameter where you could control the resolution of both your Grid 2D and your render targets. But for now, it's good enough just to be able to input it manually just for these experiments. And the other way that you can create something is actually in a module itself, where if you dive into the module, if you add a parameter, new Grid 2D collection, and set the scope to emitter, then when you can actually create a Grid 2D collection here. Add Grid 2D collection parameter, not parameter. Oh, well, I'm not, yeah, I think if you can make one. No, you can't make one. Okay, so ignore that. I'm just going to create, you can create one here actually. Grid 2D collection. Yeah, if you just create one here and connect it through, then it should appear over here. So there's, I'm getting an error. No, that's from the last time. Okay, so yeah, you can create one inline, and if you write to it, then it will add it to the collection. Basically, if you reference it, it will create one for you. Okay, so that gets that out of the way. Now let's get into how I actually manipulate the data in a Grid 2D collection. So there are these things called simulation stages, which if you over here you have these stages, which are the kind of the inbuilt ones, the ones that Epic provides for you, but you can add your own simulation stages which kind of run in this order, and within them you can have your own modules that are basically these kind of mini graphs that operate on data. So to enable simulation stages, you have to come to the emitter properties and then come down to where I hit the little down button, and then you'll see this little simulation stages section, and you can enable simulation stages and turn that on, excuse me. And that will give you these things down here. And then what you do is you just click and add simulation stage. I'll do one now. You make a generic one, and you give it a name. So this might be emit into grid. And from there, you can kind of drag it up into be in the right order that you want it to be into. But I already created this one. And then from within there, you can click the simulation stage, and you can have modules that are actually assets in your content browser. But if you're just experimenting, then it's quite nice just to use the scratch pads. And for all of this, I've just been using scratch pads and just kind of keeping them as kind of local to the system that you're in. So you just click new scratch pad module. That'll add a new one here, and you can just dive in and start doing stuff, which is quite nice. So here's the one where we emitted into a grid, and I'll just see if I can make a bit more space here. Don't actually use this bit of the interface much, so I'm just going to close that there, and I'll move this over here. Okay, so what we've done in this module is I forgot to mention that on the simulation stage itself, you usually specify which data interface you are iterating over. So particle systems are data interfaces, Grid 2Ds interfaces, Grid 3D, and there's neighbor Grid 3Ds, which is used for looking up neighboring particles, that kind of thing. as an acceleration structure. But for this, we're iterating over the grid 2D that we created. But what we're also doing is we're passing in as an input. So if you just click here and choose an input, this module scope here, which you can actually change with this change namespace, this input scope means that it acts as an input to the module, which you can set from outside. So you could set this to emitter, and it would pick up that particular one. But I've just found that doing this and then adding it as an input is more flexible if you have multiple grids kind of around and you want to change things up and experiment by changing which grid you're using. It also makes it more generic in that if you have a generic module that you want to save off and share with other people, it's nice to have these inputs so that they can input their own grids without having to explicitly set the name and it have to be in that emitter. Anyway, what this does, the reason why we are iterating over the grid and also passing it as a parameter is that we need to be able to access kind of functions on this grid 2D collection. So here we want to be able to like maybe get the resolution or convert between different indexing spaces. And what we're doing here is, in this case, we're taking the execution index, which is a linear number from 0 all the way up to however many voxels there are. And it maps that to this UV space, which is this unit kind of 0 to 1 mapping of the grid. So typically, when you run a module, it's basically a compute shader where each kind of element of the thing that you're operating on, like whether it's particles or grids, which in the case of grids would be voxels, would get its own thread. So they all run in parallel. Each module runs kind of once per element, and they all have their own execution index. And the hardware is free to kind of submit the work to the GPU in any way it wants, but ultimately they all have their own unique thread sort of index. But the way that we relate that, the way that you relate which current thread you're in to where you are in the grid is done with this. So thread number 57 might end up, at like somewhere in the middle, and you want to be able to get the position of that within the grid, and that's what this does. It gives you your position from 0 to 1 in X and Y. And then what we do is we subtract a number from that current position, which gives us kind of an offset into kind of the center of the grid. And from there, we get the distance from the current position. So if we do this subtraction, then 0, 0 basically becomes somewhere here. And the length now from that position is going to be the distance from 0, 0. And then what we can do is we can run that through a threshold, and we just say if that distance is less than 0.1, then you're inside that radius. And then we can run that through this condition node, which says that if the condition was true, if you're inside the radius, then output a value of 1, and if it's not, output a value of 0 everywhere else. And what we're doing is we're just setting that density value in the grid. So because we're iterating over the grid 2D, then this, when we write to an attribute called density, if we mark it with this stack context sort of scoping, then in the context of data interfaces and grid 2Ds, it's going to write to an attribute on that. So this stack context thing is a bit weird, but it just means that depending on where you use it, it does a different thing, and they do persist from frame to frame. So you're writing to kind of a value that's going to be there in the next frame. It'd be nice if this could be explained a tiny bit more, but for me, I've just been using stack context in the for grid 2Ds, and it's been working fine. So what we're doing on this simulation stage is I've ticked on this. Here we go. Emitter reset only, which means that this simulation stage is just one. It runs once right at the beginning, and then it doesn't do anything else. So it emits this circle, and then doesn't emit any more after that. It just runs once. So then we're moving on to this next simulation stage, which if I open up the Scratch module in there, this one does run every frame. And actually I'm going to change this to 30 just so it's a bit cheaper to sort of scrub back and forth. What we're doing is we're taking that same grid 2D collection and we're sampling from it. But what we're doing is we're sampling it at a different position from where we currently are. So where we currently are is this position for every single sort of thread. And then what we do is we subtract a value somewhere else and sample there and then write it back into density. So we're doing this thing where we're seeing where we are, moving that position, sampling it and pulling it into that current position. And that's what we typically call like a backtrace advection. And what we're using as that kind of sample offset is I'm just making up this vector, which is some value in y multiplied by 0.2 times dt. So we're just kind of making it adaptive to frame rate. So this is kind of like an arbitrary kind of scaling on this vector, but we do always want to make it adaptive to time. Otherwise, your frame rate will change the behavior. So yeah, this isn't kind of doing anything physically correct. It's just a nice kind of arbitrary advection in the up direction, and that gets us like a real simple something moving in our grid, which is quite nice to see. So that was kind of my first kind of experiment, just to get to grips with the mechanics of how this all works. And then what we're doing here is, because I've created a render target as well at the same resolution as our grid, this module simply takes the grid 2D collection, and we are getting the density value at the current position. So let's try and explain this a bit better. We're iterating over the render target this time. So this isn't iterating over the grid. So what we're doing is we're getting our index, which is a 2D index, an integer index of like the current position in x and y. And then we are finding out the resolution, and we divide by that to get a unit position, because I don't think that the render target has a unit function. So I had to kind of create this little quick, these things here basically create that kind of equivalent unit transform for render targets. We turn that into a vector 2D and we just sample at that same position. And this is actually quite nice because it also means that technically the grids don't have to be at the same resolution. You can actually sample at a different sized grid, although then you're susceptible to things like aliasing. So unless you downsampled that and did some interpolation and averaging, then you might get some issues. But then the one difference that happens with render targets is that instead of writing to the output map, here's the input map, instead of writing to an attribute in the render target, this actually calls a function node. So we're actually using that index and telling it where to put data. So we're saying, right, at this current index, put this value. So then now we can actually use the sprite render, which I've set to the emitter mode, which basically just creates one sprite for the whole emitter. And I've got this fluid material, which takes a render target as a dynamic parameter. So that means that we can, in the Niagara system, down here on this sprite renderer, set this parameter and set it to be the actual render target. And that is how we could see this. We're actually viewing the render target being rendered on the material, where the material is set up here. Now let's move on to the next Niagara system which I created. Okay, so now let's move on to this set velocity one. So this one was seeing how we could maybe sample some kind of random velocities and use that for advection instead of this kind of constant just vertical direction. So we have this advection module, and here what we're doing is I've actually added a new input parameter on the module, which is a texture sample parameter. And again, this kind of creates one locally for us So we don't actually have to set it as like a texture sample attribute or anything. We just have it on the module, and then we can give it a asset from the content browser. And then what I'm doing there is I'm doing 2 texture samples here. Make a bit more room so we can see what's going on. Yes, I'm doing 2 texture samples here, and what I'm doing is I'm taking that sort of UV sort of index space, multiplying one of them by 0.6 and another one by 1.6, and to those I'm adding this kind of constant vector multiplied by age. So what we'll get is this kind of panning in a sort of particular direction over time, and we're adding those 2 together and using that to sample the texture basically. And then we have to do this thing where we have to break the value and remake it for some reason. I don't know why I did that, but the texture sample for some reason outputs a float 4 value, so we have to turn that back into a 2D value. And then I'm doing this sort of constant bias scale type thing where, because the texture is a colored texture, which is like 0 to 1, I want the vectors to be sort of -1 to 1, so they're random in all directions. So multiply by 2 and subtract 1 takes 0 to 1 and makes it into the -1 to 1 range. And then what we do is I multiply one of them down a bit just because I don't want it to be as strong. Add them together, add 0.3 as a kind of, again, another sort of vertical buoyancy type vector thing. So it's not just random vectors, but it's got a sort of vertical component. And what I do then is I multiply that with dt so that we're adaptive to the frame rate, and take our current position and subtract that random vector. And then we sample the density and write it back in. So that gives us this kind of really fake smoke kind of looking effect, which, you know, it's not physically correct or anything, but if you're in a stylized game, this might be a way to get some kind of campfire or something. Okay, so let's move on to the next one, which is my initial attempt at a buoyancy system that was kind of more physically accurate. So let's move that to the side, move that over. So now what we have is we have our buoyancy thing here. Okay, so what I was doing initially was trying to sample the density and use that as the buoyancy sort of strength. So a lot of buoyancy systems in fluid solvers sample the density and use that as a way to kind of signify that this area needs to rise or fall depending on what sort of coefficient you put in. But that's not enough in this system, because if it's in a region of space out here, it doesn't necessarily know that there's density from below pushing up, because there's no kind of rising pressure force or anything. So what I initially did is did this kind of smoothing attempt where it would sample above and below the current voxel and then average them out by dividing by 2. And then what we would do is multiply by some strength, multiply by some dt, and then we can either add that to the existing velocity, or we could even just kind of explicitly set it and have it reset every frame. But what we're doing here is we're actually introducing these 2 new float channels, which is the velocity in the x and y direction. Now, since you can't, well, I don't think you can have vector 2D channels, just having 2 float channels is actually quite nice when you're doing fluid solvers, because when you advect velocity, you tend to want to advect the channels individually as well. But anyway, we're introducing these velocity channels, and in the end I kind of just settled back on doing, for this case anyway, just a constant value, which is again is multiplied by dt, and then some artificial strength sort of parameter that the user can change on the module, and then I add that to the existing velocity y and then just set it back. So again, this kind of feedback system of velocity being added in. And yeah, this whole system was just to experiment ways of how do we do buoyancy. And then with advection, I took it a little bit further in this case, where before we were just kind of subtracting some arbitrary vector, but what we want to do really is advect according to some defined units, where when we're adding a buoyancy, we're adding buoyancy in terms of units of the grid, and then when we advect, we want to respect those units, so that if we wanted to interpret this as like if we wanted to say that each voxel was, say, a centimeter or 2 centimeters, then we want to put in a buoyancy value that would be where the velocity represents meters per second, and then when we read those velocity values, we know how far in the grid that represents in terms of distance. So we have to respect that unit, and the way that we do that is we take the index space, and in this case, because I haven't actually defined any kind of length scale, what we're saying is that each voxel has a unit length of 1. So we don't have to do any kind of adapting to different physical scales in this case. We can just treat the index space as the unit itself. And that means that we can take the current position in index space, and then when we sample the velocity, that's also in index space. So that means that we can simply multiply by a TT and subtract in index space before we convert over to unit space for sampling. And that's quite important when we get to when we do want to actually integrate this into a real world situation in a game where we want to say that these voxels actually represent some length, then we would have to do some manipulation here of length scales, but that's getting ahead of ourselves here. We're just kind of learning the basics, aren't we? So let's subtract the position. We've sampled, we're going to the right position in index space, and then we have to do this thing where I want to convert to unit space. So I break that 2D vector into 2 index floats, and use that to convert. Use this node to convert into unit space, which is that 0 to 1. And this node knows how to do that. And then we want a 2D vector, but this node outputs a 3D vector, so we kind of have to use these two to kind of just split and then re-output a 2D vector. And this is probably where it's worth kind of adding like a 3D to 2D cast here or something, or little function helper here, which might be useful. And then I want to clamp, because if the velocities are outside of the current grid bounds, then I don't want to kind of sample it out into nowhere. I want to kind of limit that to the actual bounds of the grid itself. And then we sample the density and write back. And one thing that's nice about Niagara is that it takes care of the source and target grids for you. You might have noticed that I've not had to create any like source grid and target grid and swap between them when we advect. That's all taken care of for you behind the scenes. But that does have some implications for performance, which we'll see in a bit soon, because the more channels you add, there can be a performance effect on that. So I'll talk about that soon. Let's just carry on. Okay, so moving on, let's go to the Turbulence system. Okay, so here was me really just putting the last two kind of ideas together, where we have a buoyancy system where I'm just kind of adding a constant value. Yeah, you can ignore all the mess at the bottom. This is just the experimental stuff. Yeah, there's all this stuff here where it's just a constant value adding to the velocity, and then turbulence where we're sampling this texture again and we're multiplying it by dt and adding to the velocity here, and then taking that final velocity and doing advection. So the same kind of thing where we're in index space, subtract the velocity times dt, then convert to unit space, and then sample the density, and there we go. And in this case, I'm not actually advecting velocity yet, because when we're not doing a physical solve, these kind of things again can get you most of the way. You don't need to do an actual self-advection of velocity. And if you do advect velocity itself, which is a bit weird because you're advecting velocity with the velocity. Unless you do something to correct for that sort of fluid mechanical approach, then you're going to end up with a real messy velocity field that you can't use the next frame. So sometimes it's just good to explicitly just set the velocity each frame and then just use it rather than self-advect. So then moving on, we come to divergence. So this is where we're getting to the point where, right, we have something, stylized and semi-plausible, but we want to have something that is more physical now. So what we do is we have this thing which measures divergence. Now, this is the thing that measures how much sort of fluid is traveling into any one region of space, and also like how much is going out of that region of space. So if you've got more fluid flowing into a region than there is going out, then you've got a build-up, which technically, from the laws of physics, isn't really possible. The idea of the physics equations is that you want to conserve mass, and if you've got more flowing into a region than there is flowing out, then that's breaking the laws of physics. And in the same way, you can't have fluid all flowing away from the same region with nothing to kind of fill it in, because then you're making stuff from nothing. So what you want is your divergence to be zero, so that the net flow in is the same as the flow out. And one thing that I should probably point you towards is this page, the GPU Gems chapter 38, fluid simulation chapter, which is a really great introduction to fluid solving on the GPU and just fluid solving in general, because it gives you this real nice just introduction to the concepts and the terms and the sort of geometric mathematical intuition behind what's going on, and gives you the kind of the mathematical notation and what the actual calculation of those things in concrete form looks like, how you actually perform these mathematical operations in a kind of a practical way on a grid. Because these mathematical operations, they take place in some kind of continuous, smooth, infinitely kind of detailed world, whereas we're on a grid and we're kind of approximating that smooth world. So these things are an approximation of these kind of more rigorous mathematical definitions. So we come to divergence here, which is defined as the difference in the velocity in one direction plus the difference in the velocity in the other direction. More technically, they're partial derivatives, but we can just consider them changes in velocity. And then what you do is, to do that, you get your grid, you get your current index, and then you add one, and you go to the voxel above and below you, and you sample the velocity. Okay, it's not above and below. This is to the right and the left, and we're sampling the velocity in the x direction to the right and left of you. And then when you subtract one from the other, that's the same as this thing here, where you subtract the I plus 1 means the one to the right of you, and the I minus 1 means the one to the left of you, and then j is just the y coordinate. That's the difference in the x direction. And then you subtract it by 2, because remember how I mentioned how you have a unit length associated with your voxels? Now, because we're just because we're assuming that our voxels have a length of 1, there's no kind of physical unit associated with it. We can just divide by 2, which is nice and simple. And when we get on to making this into a kind of a thing we can put into a game, we'd want to have some sort of voxel scale here. And then we do the same thing for the y direction. We just sample above and below, and divide by 2, and then we add those two things together. And that is our divergence. That's it. It's as easy as just measuring it and writing it to a channel. And then we can actually use this divergence in the next one, which I'll show now. So let's go to our pressure solve. Okay, so this is the thing that's actually going to correct for that divergence, because you don't want a velocity field that has divergence. You want to advect with one that doesn't, and that's what gives you that kind of fluid effect. And the way that you can solve for this divergence is you have a velocity field which is divergence free. That's what you want. But what you currently have is this W which has divergence. It's got stuff in it that's, there's stuff flowing into regions where there's not enough flowing out. So we have this kind of field that doesn't meet the conditions that we want. And the way that you get that is you subtract another vector, which happens to be the gradient of a scalar field, P, where P is some kind of imaginary pressure that is we want to find this P such that when we subtract its gradient, then it makes our field divergence free. That's what we're going to do. And we don't know what this P is yet. And this article gives us a way of computing P based on what we currently know. So divergence, we knew everything up front. We could measure the velocity, do the calculation, and set the divergence. But with P, with this pressure field, we don't know how to do that in an intuitive way up front, because you could technically create a P for a voxel. It's possible to do that by solving some equation locally, but that wouldn't necessarily make it the right P for the next neighboring voxel. So you can go and correct that one, but then you've got the one next to that, which isn't going to be right. So you've got this game of whack-a-mole where you're trying to come up with all these guesses for P that don't really make sense globally. They all have to be the right P for the whole system, for every single voxel. And that's kind of where you have this kind of global solve, where the idea is that when you want to get advanced, you can put all these things into a matrix, and you have this kind of AX equals B situation, which is a way of putting the problem into linear algebra mathematical kind of technique, where you fill up a matrix and you know the divergence and you want to find this P, and that's one way of doing it. But the easy way of doing it on the GPU is to use this kind of Jacobi iteration technique, which is really easy to implement on the GPU, which is what I've done here. And what it does is it involves running this equation. This is the discrete form of the Laplacian, which is the operation that we want to do to find this P. But what we want to do is, it's rearranged a bit down here. Here we go. So you get your pressure, you basically kind of take a guess and you iterate it over many times, and over time, over the course of doing these iterations, you approach a value that's closer to the value that you want. So here we have these x's, which is your pressure values, which you first initially put in as a 0 or some other kind of best guess, and these are your neighbors. And then there's this AB term, which is actually the negative divergence. So we do a subtract divergence and then divide by this B, which is 4. So, and that gives you your next iteration of pressure. And then in the next iteration, you reread those values, and over time it kind of converges on this ideal kind of value. So here's what's happening. Let's dive into the pressure solve. Yeah, I probably didn't explain that the best, but I'll probably do a separate video on that. So we clear the pressure, so we just set it to 0, and here we go. We sample the pressure at the right and to the left, and above and below, and we add them together, and then we subtract divergence, which if we had some length scale, we'd have some kind of length scale multiplier here, divided by 4, and then we write to pressure. And then the way that this iterates is on the simulation stage itself, you can actually set the number of iterations. And the more you do of these, the more accurate your solve is going to get. So what's happening, if I set this just to one iteration, it's going to get one guess at pressure, and it's going to it would have spreaded that information kind of just to the neighboring voxel, which is not good enough really, because we won't have a correct pressure value for the whole system. So the more of these you do, if I crank this up, you can see how that pressure field spreads out a bit more. And if I do it again, then it spreads out even more. And the more of these you do, then it's going to reach this pressure field, which when you take its gradient then and subtract it from velocity, it's going to give you a divergence-free velocity field. And you can kind of see gradient here is going to, if you get the highest value and draw a line towards the lowest value, you get this kind of like vector, which points towards the kind of, the steepest descent. If you kind of look at maps of with contour lines, then you can imagine going up a hill, and the steepest bit of the hill is the direction that you travel in to get to the peak. Here it's kind of the opposite, where we've got this vector which is pointing at the steepest point downwards. So the kind of the least path of resistance, that's the gradient. So this isn't actually advecting. I turned it off for this one because it wouldn't do any good, because we haven't actually done the final step yet, which is subtract that gradient. But here it's nice just because we're accumulating divergence, we're calculating the pressure, and I've actually got this. This is a material that's previewing the pressure, and the way that I'm doing that is exactly the same as for the density, but I'm writing into just another render target. And what's nice is that because this is negative pressure here and positive pressure here, in the material I'm actually doing this thing where I'm sort of recolorizing based on whether it's negative or positive, so you can see where that negative and positive pressure is. So yeah, so let's go to the next one, which actually subtracts the pressure gradient. Let's move this a bit higher. Here we go. So subtract the pressure gradient. It's another really nice, easy operation where you look at your neighbors. This is a very common thing, very common operation that we're doing. We're looking at our neighbors, we're sampling the pressure to the left, to the right and the left of us. This is the wrong one, sorry. Here we go. So we're sampling the pressure to the right and left of us. I'll explain what these do in a minute. We take the pressure, subtract one from the other, and divide by 2. So again, very similar to the divergence calculation, but in this case, this is our gradient now. The gradient is literally the difference between them divided by the distance between them, and we subtract that. We subtract that from velocity. So we take our velocity, subtract the pressure gradient in both the x and the y directions, and that's it. You've corrected your velocity. You've projected it back down to being a divergence-free field. Now this min and max thing, this is a way of making sure that we don't go outside the bounds of the grid. So boundary conditions is something that when you get to things like collisions or the edges of the grid, then you have to do some special handling. Otherwise it's kind of, the maths gets a bit hazy as to what really happens there. So yeah, we take the number of cells, subtract 1, and then we kind of do a min and max of 0 and that values to make sure that we don't index outside of our sort of grid when we sample these pressure values. We're kind of clamping where we're sampling basically, so that if the edge voxel tried to sample outside, it would just kind of sample itself basically, which isn't the most correct thing to do. But this isn't the kind of the final version. I'll come to the final version now. Okay, so here we have everything. So I've added a couple of extra things here. What we got is dissipation. So you can see how it's kind of fading out at the top. That's a real nice thing you can actually add, where you take the sort of negative dt, basically how much time has elapsed, and multiply by -1, then you raise e to the power of that value. So if I go over to the Desmos here, this is that function basically, e to the -x, where here I've just got x is equal to time. So if your sim lasted a second, if one frame was 1 second, then you multiply your density by this much. If your sim lasted longer, it would multiply by this much. So then the fact that you have that strength parameter, it's equivalent to kind of adding some kind of constant here. So the stronger that value is, then the quicker it's going to kind of decay. And this is kind of a nice kind of analytical way of decaying stuff over time. So yeah, you just multiply your density by that and write it back. So that's how you get this decay. And then divergence, calculate pressure gradient. So here's what I'm doing a little bit extra in this version of the fluid solver. I'm doing this special advection technique, which is called McCormack advection, which does these 3 steps. And I'll actually bring up the paper because I've got it here. So it's based on this paper, and if you've used Houdini or any kind of fluid solver from like Maya, then you typically come across McCormack. I think in Maya it's called high detail solve, but the basic way it works is it does this advection forward. That's what this kind of operator does. You get this kind of intermediate value. Then you also do a reverse advection in the opposite direction. And the idea is that you reverse advect, you do this first advection, then you reverse that one that you just did. And so technically, if you do this double advection, you're going to get this error, which is, you're going to get twice the error, basically. And then what we do is we kind of take this thing and divide by 2 to kind of, we're kind of correcting for that error. So it's quite easy to implement. What we do is we do that first initial advection, which is exactly the same as we had before. There we go. So ignore a lot of this stuff because it was just me experimenting around. I need to clean a lot of this stuff up. So, and also I'll talk about this in a second. So this is the standard advection we did before. Excuse me. All we're doing though is we're writing to some temporary channel. Instead of writing back to density straight away, we write to this density hat P1. And then in the next one, we do the reverse advection. So we take the velocity, we multiply it by -1. So instead of doing a back trace, we're kind of like flipping it and advecting in the other direction. We actually sample that density hat P1 that we just created. And we write that into another intermediate channel called density hat. So we have these 2 channels now, which is the forward and the backward advection. And then in the third one, we do this kind of reconciliation step where we do that first intermediate plus the original minus that second intermediate. And that's what we do here. We take the first one, which is this density hat P1, and then from that we take the original minus that second intermediate divided by 2, and we add those 2 things together. Now this clamp thing, that's also something you have to do because this technique, it's technically not very stable in that you can end up with values that are outside the range of the density that you sampled from. So you kind of have to make sure that you keep your values within the range of your original source density. And the way that we do that is, well, one way of doing that is just by clamping the values to the source values. So we take our position that we are the position that we are sampling from, we are flooring it to get the integer positions, and then we add 1 to those, and we sample the kind of that floored voxel, then 1 in the x direction, then add 1 in the y direction, and then 1 in the kind of 1 direction. So these are the 4 voxels that kind of surround that sample position. And this density value that we originally sampled is made up of those 4 values, but just kind of interpolated between them based on like the fraction. It's just that in this case we're storing the min and the max of those 4 voxels, and we just store them in 2 different channels, which we can reference later. And I will just come back to here. So yeah, you read those clamped values in and just do a clamp at the end and write back to density. And that gets you much higher detail solves. Otherwise it can get quite dissipative. So that's kind of where I am right now. The next steps from this are going to be how I can get faster pressure solves. So if I turn on the performance and give this a bit of a play, then you can kind of see that the pressure solve is taking up like 12 milliseconds. I'm doing 64 of these. Now, one reason why this is slow is because I'm using these grid 2D collections and storing multiple channels in them, which can be quite costly because every time that you write to a channel, it actually writes all of the other channels, even if you don't touch them. So here where we're doing pressure in this one, we're constantly writing pressure, but we're also writing density and all these other channels that are created, which we don't necessarily want to do. So I need to go back and actually kind of separate these out into their own grid 2D collections to kind of mitigate that cost. And I think that the Epic devs are thinking of ways to kind of get around that. But for now, I think that's why it's so high. But also there are other things we can do. Like there's a paper called Fast Eulerian Fluid Simulation in Games Using Poisson Filters. There's a video for this as well, which is quite good. But basically what it says is that when you do that Jacobi iteration, which is this thing here, then that is equivalent to, if you do that multiple times on a single voxel, then what you get is this spread of information. It's equivalent to kind of running almost like a blur filter. And you can run this operation on your grid using this convolution kernel. And because you can do that, there's actually a really fast way of doing these convolution kernels, which just is to separate them out into these kind of 2 one-dimensional sort of arrays of values. And then you can do this sort of filter pass in 1D horizontally, and then you do the same thing sort of in this direction. This would be horizontal and vertical, and then horizontal, vertical, and then you get a massive speed up. So that's one thing I'm investigating, and hopefully I should be able to show something maybe in a few weeks, depending on how much time I get. But yeah, that is where I'm at right now with this thing, and I'm quite happy with it. It's been a real good fun project. I will probably do another video where I talk about this thing here, which is the pig head. Yeah, the ray marching shader and the shadow pass, which I'll give you a bit of a teaser. I've got a shadow pass Niagara system where you can actually see the shadow here being pre-computed. I do some sort of ray marching in a Niagara module. So the actual material itself, if we go back to here, the material itself is doing ray marching in a custom HLSL shader, and you can actually do the shadow pass onto a render target, but you have to invoke it with blueprints. So one thing I've done is I've converted that to a Niagara module, where it's just kind of invoked as part of the Niagara module. You just bake your shadow pass into a render texture, and then you feed it into the main ray marching volume, which just kind of reads up that shadow pass. But yeah, that's that. So yeah, hopefully that was a bit of fun. And if you've got any questions, just write some comments in the description of the video. Not description, just write some comments on the video. And yeah, I'm hoping to make more videos like this, because I typically want my videos to be perfect and spend a lot of time planning them, which means that they never get made because I never am able to make them perfect enough, or I never have enough quiet time to be able to make them. So I'm just going to start making videos like this where I just talk over stuff, and maybe they're not the most polished in the world, but you know, you get to see stuff, I get to make stuff, everyone's happy. So thank you for watching, and see you later.